Hello everyone, welcome to my channel Chemical Engineering Zone. So in this lecture we will discuss about absorption of sulfur dioxide from flue gases into the methyl diethanol amine. So methyl diethanol amine, this is a solvent. We will absorb sulfur dioxide gas into the methyl diethanol amine solution. So this solution will be made from methyl diethanol amine plus water. So we will prepare this solution and we will absorb sulfur dioxide gas from flue gases into this solution. We will use Aspen HYSYS to absorb the sulfur dioxide gas from flue gases into the methyl diethanol amine solution. So this is absorption column. In the absorption column, the flue gases is entering from the bottom at some temperature, at some pressure, at some mass flow rate. So we will discuss these, the parameter of flue gases. And what are the flue gases? These are the gases which are produced after the combustion of coal or some other fossil fuel. So as we know that coal consists of sulfur, nitrogen and other element. From the elemental analysis of coal, you can say that coal can produce sulfur dioxide, nitrogen oxide, carbon dioxide and other flue, some harmful gases. So these harmful gases, if go to the environment from the industries, it will create the air pollution. So in order to reduce the concentration of sulfur dioxide in the flue gases, we will absorb the sulfur dioxide gas from the flue gases into the methyl diethanol amine solution. So the flue gases is nothing but these are gases like sulfur dioxide, CO2, methane, water vapor, and these are the NOxes and SOxes. These are some flue gases. So these are produced from the combustion of coal or some other fuel. So these are the flue gases which are entering at the bottom to the absorption column. The solution which is the clean solution of methyl diethanol amine plus water. This solution is coming from the top and the flue gases is coming from the bottom. So the gases, the sulfur dioxide gas will absorb from the flue gases into the methyl diethanol amine solution, and the absorbed sulfur dioxide gas will then come out from the bottom of the column. This is called the rich solution because it consists of a large amount of sulfur dioxide gases and some small amount of other gases also, but our interest is to remove sulfur dioxide from the flue gases up to some extent. So we will see that how much sulfur dioxide can be removed in this absorption column. So this is the lean gases. These are the gases in which the sulfur dioxide amount is very small. So the lean gases, the sulfur dioxide amount will be small as compared to the sulfur dioxide amount in this gases. So this is the absorption column and there are some stages. So we will use a column. In the column there will be the number of stages will be 16. We will use the number of 16 stages. So these are the specification of the stream. There are two streams. One stream is coming from the top, which is the solution, and the flue gases is coming from the bottom. The lean gases is coming from the top, and the dirty solution or the rich solution is coming out from the bottom of the absorption column. So the flue gases, the property of flue gases, the flue gases consist of in this example, we burn coal in of a thermal power plant and we produce some flue gases like carbon dioxide. The mole percent of carbon dioxide in the flue gas is 20%. Nitrogen is 50%, 15% sulfur dioxide gas, and 10% water vapor, and 5% oxygen. The temperature of the flue gases is 60 degrees centigrade, and the pressure it is flowing at 2 bar pressure, and the mass flow rate is 1300 kilogram per hour. And the solution which is made from methyl diethanol amine solution plus water. So we take water and we mix some methyl diethanol amine solution At 30% is methyl diethanol amine solution by mass percent, and 70% is water. So 30 to 70, 30% and 70% are methyl diethanol amine, and 70% is water. The temperature of the solvent is 23 degrees centigrade and pressure is 1.2, and the mass flow rate of the solvent is solution is 2700 kilogram per hour. This is the temperature of solution, this is the pressure of solution. So the temperature of solution is 23 and pressure is 1.2 bar. So 23 and 23, this is the solution. The temperature is 23 degrees centigrade at room temperature, and the pressure is 1.2 bar, and the mass flow rate is also given in the question. So our main focus is how can we absorb the how much SO2 can be removed from the flue gases into the solution. So we will use Aspen HYSYS to absorb sulfur dioxide from the flue gases. So come to the Aspen HYSYS and add the gases. So there are come to the search for so first of all we will add the component of the flue gases, which is carbon dioxide. So carbon dioxide, similarly add nitrogen, add sulfur dioxide, water, and the other is oxygen, and methyl diethanol amine solution. So methyl, MEDA, methyl diethanol amine solution. So MDEA amine, methyl diethanol amine, this is methyl diethanol amine absorbent. So these are the component. Now in order to produce acidic environment in the absorption column, we will add some other component. Other acidic component like H2S, hydrogen sulfide, and H2O2, hydrogen peroxide. So we added these components. These two are added for producing acidic environment in the absorption column. So next we will go to the fluid package. In the fluid package, then we will add the fluid package. Click on add. It will take some time. So these are the fluid package. So this is the acidic gas, chemical solvent, liquid treating, and the physical solvent. So chemical solvent, we will add chemical solvent, which is methyl diethanol amine solution. So we will add this one. We will come down to check it is okay. So the property package is okay. Then we will come to the simulation. So come to the simulation environment. It will take some time. So we will go to the simulation environment. It will take some time. So it is loading. Simulation environment. This is the simulation environment. So in the simulation environment, we will come to the separator, because absorption column is a separator. So we will come to the, this is the absorber, and this is the two inlet and two outlet. So this is click on it, drag it to the simulation environment. So it will take some time. So this now add two material stream, one for the solution and other for the flue gases. So the flue gases. Now close this environment and click on the solution, which is the methyl diethanol amine solution. So the solution name is, this is the solution is coming from the top. So the solution, this is the solution. So we will clean solution, or we will add solution. This is the solution. solution. The temperature of the solution is the temperature is 23 degrees centigrade. The temperature is this is the vapor pressure here is 0, you can add because this is only and only liquid. So this is the temperature is 23 degrees centigrade, and the pressure is the pressure of solution is coming to the absorption column at 1.2 bar. So from kilopascal we will convert into bar. So 1.2 kilopascal is equal to 120. This is 1.2 bar is equal to 120 kilopascal. So this is 1.2 bar, and the mass flow rate of the solution is 2700 kilogram per hour. So 2700 kilogram per hour. So this was the so unknown composition. Let's show that unknown composition of the solution. So how much the MDEA and water is present in the solution. So it is given in the question. So come to the composition, and in the composition methyl diethanol amine is how much percent? It is about 30% methyl diethanol amine. So 30%, but mass, it is mass percent. So we will click on the mass fraction because it is weight fraction. So 30%, click on it. And how much water? 70% is water. So 70% is water is 70%. The other are 0. So there is no CO2 in the solution, there is no nitrogen, there is no sulfur dioxide, there is no oxygen, and there is no hydrogen sulfide and H2O2. So click on OK. Sum of all is mass fraction is equal to 1. So click on OK. So this is OK. Now the stream 1 is fully specified. Now close it. Solution 1 is fully specified. Now come to the stream number 2, which is flue gases. So these are the dirty gases, because these are the dirty gases which consist of various harmful gases which can produce a lot of diseases in animal and human beings. So the solution 2, name of the solution 2 is the flue gases or dirty gases. So this is the flue gases or dirty gases. So dirty gases or flue gases. Now the temperature of the flue gases is given in the question. So the temperature of the flue gases is 60 degrees centigrade. It is 60 degrees centigrade, and the pressure of the flue gases is at 2 bar. So it is at 2 bar, which is 200 kilopascal. So this is the 200 kilopascal or 2 bar. Now the mass flow rate of the flue gases is the mass of the flue gases is 1300 kilogram per hour. So 1300 kilogram per hour. So this is show us error, that unknown composition. So what are the composition of the flue gases? So come to the composition, and these are the various components of the flue gases. So in the flue gases, the carbon dioxide mole fraction is 20%. So 20% carbon dioxide, 50% nitrogen. 50% is nitrogen, and sulfur dioxide is 15%. And water is 10%, and oxygen is 5%, 0.05, and H2S, and these are 0. We will ignore these. So these are 0 just to create acidic environment. So click on OK. Sum of mole fraction is equal to 1. So click on OK. So this is OK. The flue gases condition is, the stream is also fully specified. This is the dirty gas or flue gases, and this is the absorption column. So double click on the absorption column. So the column name, so you can change it. This is the absorption column. Absorption column. absorption column. The inlet stage is the solution is coming from the top. This is the top and this is the bottom, and this is the top vapor and this is the bottom liquid. So the top from the top, the solution is coming from the top, which consists of with methyl diethanol amine, methyl diethanol amine plus water solution. So click on solution, and there is no inlet or side stream, only the solution is covering from the top. The bottom stream is the dirty or flue gases. So flue or dirty gases, this is, click on it, add, and the overhead product. So in the overhead product, this is the lean gases, and this is the dirty solution, which consists of a large amount of sulfur dioxide. The sulfur dioxide from this stream, from this flue gases will absorb, and it will coming out from the bottom of the absorption column. So the lean gases will be coming out from the top. In this gases there will be less amount of sulfur dioxide as compared to in this stream. So this is the lean gases, and this is the rich solution. So the inlet liquid is inlet liquid, and this is the so next, come to the next. Now the top pressure. Now what is the top pressure? What is the top pressure? It is given in the question that there are 16 number of trays. So go to previous, go to previous to add the number of stages. This is 10 number of stages. So in the question there is 16 number of stages. So 16 number of stages. Go to next, and the top pressure. The top pressure is 1.4 bar. 1.4 bar. The top pressure is 1.4 bar, and the bottom pressure is 1.6 bar. 1.6 bar. Remember, in the absorption column, the bottom pressure is high, is large as compared to the top. So this is the 1.6 bar. 1.6 bar. Next, these are the optional temperature, so don't give anything. So click on done. So now this is the now come to a simulation environment. Just double click on it. Double click on it. Come to the, this is the connection, and this is the parameter. This is the worksheet. So this is the worksheet, and this is the flow sheet. So come to the design, and the inlet, this is the solution and the dirty gas, and the overhead product is lean gases, and this is the rich solution. So this is the rich solution. Now solve it. So run the simulation. Click on run. So column feed stream solution is entering the tower below stage pressure. So the column feed stream solution is entering the tower below stage pressure. So the solution pressure is less than the stage pressure. Okay. So it will take some time to solve. So it will take some time. Now it is solving. Converge. It is converge. So this is the absorption column. It is fully converged. Now in order to obtain that, in order to define that how much CO2 is absorbed from the flue gases, so double click on the column and go to the work. So go to the worksheet, and this is the, and come to the composition. So this is the solution of diethanolamine, and this is the dirty gases percentage, and this is the lean gases, and this is the rich solution. So in the dirty gases the sulfur dioxide was 15%, and in the lean gases the sulfur dioxide is about 7%. So it is about 15 minus. So if you determine the percentage of SO2 removed from the flue gases, you can obtain 0.1500 minus 0.0729 divided by 0.1500. So this is about 50% or 53% sulfur dioxide is removed from the flue gases. So I am checking it that whether it is 50% or 53. So 0.1500 minus 0.0729. So you can check it in your calculator. So divide by 0.1500. So it is 51%. About 51% sulfur dioxide is removed. Now how can we increase the removal percentage of sulfur dioxide from the flue gases? So there are many ways. We will discuss one way. You can increase the solution mass flow rate in order to increase the percentage removal of sulfur dioxide. You can also check the removal of carbon dioxide. This is the 20%, this is 18. So about 2% is decreased. So a less amount of carbon dioxide is also absorbed into the solution from the flue gases. So you can increase the sulfur dioxide conversion. So come to the solution. We can if you increase the mass flow rate of the solution, then what will be the effect? So I think it will increase the removal percentage of sulfur dioxide from the flue gases. So if you increase the solution mass flow rate, it will increase the removal percentage of sulfur dioxide from this stream. So click on the solution, open it, and the solution is 27 kilogram per 2700. So I am just increase it to 4000 kilogram per hour. So what will solution? So it is okay. Now close it. So it is fully converged. Now double click on the column and come to the worksheet, come to the composition, and now check in the dirty gases the sulfur dioxide is 15%, but it is here in this it is 0.001. So how much SO2 is removed? It is 0.1500 minus 0.0001 divided by 0.1500 multiplied by 100. So it is about 93. It is about 93%. So I am checking it in my calculator. So 0.1500 minus 0.00001 divided by 0.1500 0.1500. It is 99.93% removal. 99.93% SO2 is removed, and here it is about from 20 to 16%. So further carbon dioxide is also further decreased and it is further removed if we increase the mass flow rate of the solution. So this was introduction. This was a problem related to the absorption of sulfur dioxide into the flue gases, into the solution, from flue gases into the solution. Thank you very much for your attention. If you are new to the channel, please like and subscribe.